Okay, so let's do one more example. Here we have a cylinder as a container, and we have inlet. The mass flow rate is m dot I, and it's equal to 15 kilogram per second. At the same time, you have outlet, and the mass flow rate at the outlet, m dot E, is not a constant, but 4 times L. It's a function of the height L of the liquid inside the container. If the liquid has a height of L, and then the mass flow rate m dot E leaving will be 4 times L. Okay, and the cross-sectional area of the cylinder is A equal to 0.5 meters square. And then our control volume, the system, is the liquid itself. Initially, when time is equal to 0, the height of the liquid inside the container L is equal to 0. And we want to find out the height L of the liquid as a function of time if the density of the fluid rho is equal to 1000 kilogram per meter cube. Okay, so let's do it. Okay, so we're gonna start from conservation of mass equation again. Sigma m dot I minus sigma m dot E. Right hand side is d mcv over dt. Okay, so can we still get rid of the right hand side this time? No, we cannot because the problem didn't say it's steady state. So right hand side does not go to 0 this time. You just have to keep it. Okay, but the good news is we only have one inlet and one outlet. So there's no need for us to use the sigma sign. So m dot I minus m dot E, and then right hand side d over dt. Okay, so what we're going to do is to rewrite the mass of the control volume. Because we're looking for length L, we want to have L show up in my equation. But at this moment, L still doesn't show up. So let's find a way to have L show up in this equation. How do we calculate mass of the control volume? Mass is equal to volume multiplied by density. Volume multiplied by density. Okay, so we know density of the fluid is rho. How do we calculate the volume of the control volume? The volume has the shape of a cylinder. So how do we calculate the volume of a cylinder? Cross-sectional area A times the height. And the height of the liquid is L. So now we've rewritten MCV to AL rho. L shows up now in my equation. Okay, so let's plug in m dot I. M dot I is equal to 15 kilogram per second SI unit minus m dot E. M dot E is 4 times L. And take a look at the right hand side. Capital A, cross-sectional area is constant. It's a constant. What about rho? Density of the liquid is also a constant. So if those two are constants, you can pull them out. It becomes A times rho. What is left is dl over dt. Okay, and now let's plug in A. A is equal to 0.5 meters square SI unit times rho. Rho is equal to 1000 dl over dt. So now the equation becomes 15 minus 4L, and right hand side becomes 500 dl over dt. Okay, so now it's very obvious. This equation is an ODE, ordinary differential equation. And the way we solve an ODE is by separation of variables, meaning you move everything regarding L to one side and everything about T to the other side. So let's do the algebra. We move dt to one side and everything else to the other side. It's 500 over 15 minus 4L times dl. Okay, so this step is purely algebra. Move the two variables into each side. Okay, so now what we're going to do is to do the integral. Integral left hand side, integral right hand side. Okay, left hand side is very straightforward. Integral dt just becomes t. And then let's do the right hand side. So first of all, 500 is constant. You can pull it out. 500 integral 1 over 15 minus 4L times dl. Okay, so now let's continue. How do we solve the right hand side? How do we solve this right hand side? We can do this. Let's continue. 500 times integral 1 over 15 minus 4L differential. Okay, so what I'm going to do is, first of all, I'm going to multiply L by -4. Multiply L by -4. If you do that, in order to keep the equal sign still valid, you have to divide the right-hand side by -4. -4 cancels -4, so the equal sign is still true. And next one, what I'm going to do is to add a 15 before -4L. I added a 15. In order to keep the equal sign still valid, do I need to minus 15 somewhere? The answer is no. Why? Because take a look. What I am essentially adding is differential 15. And differential constant is constant. D15 is 0. D15 is 0. So I added 0 to the right hand side. So there's nothing I need to do. So that's it. Okay, so this equation becomes negative 125 times 1 over 15 minus 4L times differential 15 minus 4L. Okay, left hand side is still T. Okay, and then what is the reference we use from your calculus textbook? Integral 1 over x times dx is equal to natural log x. So we're going to apply this reference to my right hand side. And what is the x for my problem? The x for me is 15 minus 4L. So now we can rewrite the right hand side into negative 125 and now natural log 15 minus 4L. Okay, and do not forget, if you do not integrate with limits, then you're going to generate one constant, so plus c. Okay, so now we just need to look for c. How do we look for a constant? We need initial condition. Initial condition. Initial condition is given when time is equal to 0, the height of the liquid is also 0. So we're plugging this initial condition back into this equation. Left hand side becomes 0, right hand side becomes negative 125 natural log 15 minus 0 plus c. And so from here we can find the value of c. Constant is equal to 125 times natural log 15. And then we can plug in this c back into our general solution. So our particular solution is t equal to negative 125 natural log 15 minus 4L plus the constant, which is 125 natural log 15. Okay, so they both have 125. We take 125 out of it, so it becomes natural log 15 minus natural log 15 minus 4L. Okay, we can further simplify the right hand side to natural log 15 divided by 15 minus 4L. Natural log A, the reference is, just in case you don't know, natural log x minus natural log y is equal to natural log x over y. Okay, just in case you don't remember that. Okay, so now that's our left hand side, t. Okay, next we just need to do some algebra because the question is looking for L as a function of time. So you should have L as the left hand side and everything else to the right hand side. Okay, so now we can move 125 to the left hand side. T over 125 is equal to natural log 15 over 15 minus 4L. And then we can do that. Exponential function t over 125 must be equal to exponential function natural log 15 over 15 minus 4L. Okay, and left hand side is still e with the index of t over 125. Right hand side, exponential function natural log, they cancel each other. So what is left is 15 over 15 minus 4L. So now everything is very easy. You just perform algebra and move L alone to the left hand side. So right hand side becomes 15 over 4 times 1 minus exponential function with the index of negative 0.008 times t. That's it. That's our solution. The height of the liquid L as a function of time.